Welcome to this in-depth exploration of executable binary formats. Today, we'll delve into the fundamental differences between Windows Portable Executable, or PE, format and Linux's Executable and Linkable Format, widely known as ELF. These formats are the blueprints that operating systems use to load and execute programs, defining how code, data, and resources are organized within a file. Understanding their structures is crucial for anyone working with system-level programming, reverse engineering, or cybersecurity. We'll uncover how each format dictates the process of binary loading, from initial parsing to memory mapping and dynamic linking, highlighting why these distinctions matter in the real world. Our journey will focus specifically on the key differences in how these executables are structured and subsequently loaded into memory for execution, providing a comprehensive overview for a technical audience. Before we dive into the specifics of PE and ELF, let's establish a foundational understanding of what a binary executable format truly is. At its core, an executable format is a standardized structure for computer programs that an operating system can understand, load, and run. It's more than just raw machine code. It includes metadata essential for the OS. This metadata tells the operating system where the program's code begins, where its data is stored, which shared libraries it depends on, and how to allocate memory for it. Without a standardized format, every program would require custom loading logic, which is an impractical and inefficient approach. These formats facilitate crucial functionalities such as memory management, process creation, and dynamic linking, acting as a crucial interface between the compiled program and the operating system kernel. The Portable Executable, or PE, format is the standard executable file format for 32 and 64-bit versions of Windows operating systems. Originating from the Common Object File Format, or COF, which itself had roots in Unix, PE files are essentially a data structure that encapsulates all the information required for the Windows loader to manage the executable code. A PE file typically begins with an MS-DOS header for backward compatibility, allowing a simple "this program cannot be run in DOS mode" message to display. Following this, the main PE header contains crucial information, including the file header and an optional header that provides details like the entry point address and preferred base address. The PE structure then organizes the program's different components, such as code, initialized data, and resources, into distinct sections, each with its own attributes and permissions ready for memory mapping. In the world of Linux and other Unix-like operating systems, the Executable and Linkable Format, or ELF, reigns supreme. ELF is a flexible, extensible file format designed to be portable across different architectures and operating systems. Unlike PE, ELF provides a unified format for executables, relocatable object files, shared libraries, and core dumps. An ELF file begins with a mandatory ELF header, which contains fundamental information about the file itself, such as its type, machine architecture, and entry point. Following the ELF header, there are typically two tables, the program header table and the section header table. The program header table is crucial for loading the executable into memory, describing how the file's contents are mapped into the virtual address space. Conversely, the section header table provides detailed information about the file's sections, primarily useful for linking and debugging purposes, though not strictly required for execution. One of the most immediate distinctions between PE and ELF files lies in their header structures, which serve as the initial roadmap for the operating system. The PE format utilizes a two-stage header system. It starts with a legacy MS-DOS header, a relic from early Windows compatibility requirements, which then points to the actual PE header. The PE header itself consists of a file header describing the file's characteristics and an optional header containing vital runtime information, like the entry point address and image base. In contrast, ELF format employs a more streamlined, singular ELF header at the very beginning of the file. This ELF header immediately provides crucial metadata such as the file's class, data encoding, version, and the offsets to the program header table and section header table. This difference reflects their evolutionary paths and design philosophies, with PE preserving backward compatibility and ELF opting for a more modern, direct approach from its inception. The way code and data are organized within PE and ELF files presents another significant architectural divergence. In the PE format, the executable is divided into sections. Each section, such as .text for executable code, .data for initialized data, and .rsrc for resources, is described in the section table located after the PE headers. These sections are a logical grouping of data and code primarily used by the linker and for fine-grained memory protection. During loading, the Windows loader maps these individual sections into memory. Conversely, ELF files introduce the concept of segments, which are described in the program header table. Segments are collections of sections that are grouped together for runtime execution and memory mapping by the operating system loader. For instance, an ELF typically has a text segment that bundles all readable and executable sections and a data segment for writable data. While ELF also uses sections described in the section header table, these are primarily for linking, relocation, and debugging, offering a more granular view for tools rather than direct loading by the kernel. This dual perspective in ELF, segments for runtime and sections for linking, provides greater flexibility. Dynamic linking is a cornerstone of modern operating systems, allowing programs to share common libraries and reduce memory footprint. PE and ELF handle this crucial process differently. In PE files, dynamic linking relies on the import address table, or IAT, and the export address table, or EAT. The IAT is a table of pointers that the PE loader fills with the actual memory addresses of imported functions from DLLs at runtime. The EAT, on the other hand, lists functions that the current module exports for other modules to use. Relocations in PE are typically handled by fixing up absolute addresses if the preferred base address is unavailable. ELF utilizes the Procedure Linkage Table, or PLT, and the Global Offset Table, or GOT, for dynamic linking. When a function from a shared library is called, the PLT entry jumps to an address specified in the GOT. The GOT is initially populated by the dynamic linker with stub addresses, and the actual function address is resolved and updated in the GOT only when the function is called for the first time. ELF's position-independent code, or PIC, significantly simplifies relocation, as code is designed to run correctly regardless of its loaded memory address, primarily using relative addressing. The role of the operating system's loader is pivotal in bringing an executable to life, and its responsibilities differ based on the binary format. The Windows PE loader is responsible for parsing the PE header, allocating memory for the process, mapping the PE sections into the virtual address space, and performing necessary relocations if the preferred base address is already occupied. It also resolves dynamic library dependencies by processing the IAT, loading required DLLs, and patching in the correct function addresses. The Linux LF loader, often part of the kernel or implemented by a user space dynamic linker, follows a similar but distinct process. It parses the LF header and the program header table to determine how segments should be mapped into memory. Due to LF's emphasis on position-independent code, fewer explicit relocations are needed at load time. The LF dynamic linker handles resolving shared library dependencies, typically using the PLT and GOT, a process that can involve lazy binding where resolutions occur only upon first call. Both loaders aim to initialize the process environment and transfer control to the program's entry point. The underlying binary format has significant implications for system security, influencing how operating systems implement protection mechanisms. For PE files, security features like address space layout randomization, or ASLR, and data execution protection, or DEEP, are supported through flags in the PE header and the operating system's loader. The PE format also provides mechanisms for digital signatures to verify file integrity and authenticity, crucial for preventing tampering. However, PE's historical reliance on fixed base addresses has in the past made it more susceptible to certain types of attacks, though ASLR mitigates this significantly now. ELF's design, particularly its strong support for position-independent executables, or PI, inherently enhances ASLR by allowing code to be loaded at random addresses more effectively without extensive relocation overhead. This makes return-oriented programming attacks more challenging. Furthermore, ELF's clear separation of segments with distinct permissions, for example, read-only code, writable data, directly supports DEP. Both formats are continuously evolved to integrate new security features, but their foundational differences impact the ease and effectiveness of implementing these protections. In conclusion, our exploration of Windows PE and Linux ELF formats reveals that while both serve the essential purpose of enabling program execution, they do so with distinct architectures and philosophies. The PE format, with its legacy MS-DOS header and two-stage PE header, reflects Windows' need for backward compatibility and its tightly integrated approach to module loading and resource management. ELF, on the other hand, embraces flexibility and portability across various Unix-like systems, offering a more unified structure for different object types and a clearer separation between runtime segments and linking sections. These differences directly influence everything from compiler design and linker behavior to operating system loader implementations and, critically, security feature integration. Understanding these foundational distinctions is invaluable for developers optimizing performance, reverse engineers analyzing malicious code, and system administrators ensuring robust security. Ultimately, the choice and design of these binary formats underscore the unique architectural philosophies of the Windows and Linux operating systems.